Welcome back, class. Thanks for checking in again and watching some videos and trying out some of these Google Forms I've been sending out. Again, these are just opportunities, they're not required. It's one of those things I want to provide you guys an opportunity to continue your education. I think that's important. Some of you guys are going to be going on, trying, upper level stuff. And, I think this is important that we get through some of this material still, because it's obviously something we were going to cover in the year. Today's topic is a little bit different. But again, these are just opportunities. It's not required. It's just kind of it's a chance for continue on. But again, don't feel obligated. But you can try out a couple problems if you want. All right, so let's jump right in here. So here's the topics that I have. Integration by substitution is the new thing today. This is brand new. We did not do this. This is the topic we were going to do on Monday, before we had the shutdown for COVID. So we're in part 1 of week 5 here. We're still doing antiderivatives, integrals, areas under curves, but now what we're doing is we're doing it by substitution. So what's happening here is that these particular integrals, they're challenging, where it's not just easy material, where there is some issue where you can't just take a normal antiderivative like a power rule or a trigonometric function, and you can't just take an antiderivative like quickly. It's not going to be apparent what it is. So we have to do a little substitution, take out something that's complicated, replace with a different letter of the alphabet, so that makes the problem a lot easier to look at, and then you can take the antiderivative of it. I know that seems a little weird. I'll show you on the first couple. I'll start simple, and we're going to work our way to the tough ones. On the Google form this week, I think I picked up 5 problems. I think they're going to get challenging. Like, this is going to be the real first test to see how well you did. Again, you can watch this over. You can email me or whatnot. But again, we're going to try some new material here, and I think see how it goes. And again, I'll have a Zoom meet this week if you'd like some help, and we'll do some more examples. But again, let's jump right in here. So first problem that we have here, we have an example. It's the integral is x plus 1 to the third power, so x plus 1 cubed dx. And we're gonna try to look at how to find the antiderivative. So the antiderivative is the original function of this problem. So whatever the original function was, and then if you were to take the derivative of that original function, it would give you this thing again. It would give you the original problem. So the problem is, it's not just apparent like what it should be, because it's got a weird power. So here's what you do. This is the shortcut. You take out the thing inside the parenthesis. And so I'm going to take this item here, and I'm going to replace it with like w. I'm going to say w is x plus 1. Okay, I know that seems weird. I'm going to replace that with w. So on the original problem, this is what we're looking at. It's w cubed. So I've substituted it out. And then the idea is we also have to replace the dx part. The dx can't be a dx because we replaced it with a w. But dx represents the derivative of the variable. So what we have to do is, if I want to replace it with dw, I have to take the derivative of these two things, because I have to keep it balanced. It's a balanced equation. I have to take the derivative of both sides. So w, the derivative of w, is literally dw. It's the derivative of w with respect. And then the other side, the derivative would be just 1, because the derivative of x is 1. And the derivative of 1 is 0. So I'm taking the derivative of both sides, no matter what's sitting there. And so this part here is the part that I'm replacing. So I'm going to be plugging this in to the original problem. So, and the idea is that when I take the derivative of this left side, the right side here, the x plus 1, the derivative of x is 1, but it also had a dx on it. Because I don't know what x is, so I have to put it to respect to x. That's the same thing with what I do with w, right? W, the derivative of w is 1 dw. So there's actually a 1 here, dw. And now why that's important is because what I'm going to do is, on the original problem, I'm going to plug in for this dx, and technically there is a 1 in front of it, I'm going to plug in the dw right there. So you have to be able to look at this part and see that it's in the original problem, that I can substitute out and make sure it's the right letter. So dw is in that spot. It'll make more sense as we go. But again, this is what we're doing. We're substituting. Now, this is something we can do like normal. This is just a normal power rule. It makes the problem easier, so I can take the antiderivative of it. This is just a power rule. It's w to the fourth over 4, right? You add 1 to the power, and you divide by the power. And then, obviously, there would be a constant, because anytime you take an antiderivative of something, you could be left with a number behind it, because if I take the derivative of this thing, and this could be any number in the world, it would turn back into this. That's the idea. All right, so now we're not done yet. So I've taken the antiderivative, right? You add 1 to the power, divide by the power. If you don't want to add a constant, you don't have to, but I always put the plus c there. But then I have to remember that I substituted something out here. This wasn't the original problem. It didn't have w's in it. It had x's. So what I'm going to do is I'm going to take the w back out and replace it with what we substituted out. The original line that I substitute out was an x plus 1. I have to plug that back in. This is the answer for this problem. That is the antiderivative for this integral. That's the idea. So you substitute it out so it makes it easier to look at, so you can do a normal power rule or a normal trig rule, but then you have to substitute it back in the very end. So it's kind of clever the way that it works, just to prove the point that it actually does give you the correct function again. If I take the derivative, you drop the 4 out front, 4 over 4, x plus 1 to the third power, and then you take it times the derivative of the inside times 1. And so the 4's would cancel, this is a 1, that would go away, and you're left with x plus 1 to the third power. So it is the actual antiderivative. It's crazy how this stuff kind of works out the way that it does. But again, this is by substitution. Now, obviously, this one isn't the greatest example because it was kind of easy. There's really not a challenge there. It's just you just took out the x plus 1. It didn't really show why you're doing it. But the next one hopefully will. All right, let's jump to the next one. I got about 3 or 4 problems, I think, left. All right, so on this particular problem, I'm going to take and I'm going to plug the w is going to be my x squared. I know that seems a little goofy, but I'm going to use it's usually the thing in the parentheses, so x squared is going to be my w. Now, if I take the derivative of both sides, it's a dw on the left side, and on the right side, it would be a 2x dx, because the derivative of x squared is 2x, right? You drop the power up front, subtract 1 off the power, but then you have to put the dx behind it because you don't know what x is, so you have to put the respect to behind it. And you're seeing this part is right there. You're seeing it. So when I start doing this stuff, and I go to my problem, and I'm taking out the x squared and plugging in w in there, the 2x dx in the back is actually just a dw. So this is why we substitute. It makes the problem significantly easier to look at. And now we can just do the antiderivative of cosine. The antiderivative of cosine is sine plus c. Right? The antiderivative of cosine is sine. The derivative of sine is cosine. So that's the idea. So that's the antiderivative. And then the last step here is to substitute back in what w was. My w was an x squared. That was the original thing we substituted out. This is the answer I'm looking for. This is the antiderivative for that integral. It's going backwards. Now, if you want, take the derivative of this item that's in the box, and it should give you right back to what you started with. Now, derivative of sine is cosine, x squared, and then you take it times the derivative of the inside, which is 2x. Because it's a chain rule. Let's jump right in. Let's do some more challenging problems as we go. They're not going to be crazy difficult, but they're a little more difficult as we go. All right, so here's what we have. So again, just like before, I'm going to say my w is going to be my 5x plus 2. That's going to be my part that I'm substituting. If I take the derivative of both sides, this would be 5 dx, right? Because the derivative of 5x is 5. And then I have to put the dx behind it because that's the derivative with respect to. So that's the part. Now, if you look back up to the original problem, there is no 5 up here on the outside. There's no 5 by this dx part. It's not in the front. It's not behind it. It's gone. It's not there. So the idea is we have to account for that. Like, this 5 is nowhere to be found. So we have to account for it. So here's the idea. So I'm going to take out this problem. I'm going to plug the w into that parenthesis. So the w is the 5x plus 2. And then the dx, I'm going to try to replace it with a dw. But the problem is the 5 isn't counted for. So what I need to do, since the 5 isn't there, I'm going to divide this 5 over, like this. So I'm taking that 5 to the other side, and now I can replace the dx, because the dx is sitting here. So I'm going to replace the dx with a 1/5 dw. Because I have to do a perfect sub. If it's there, substitute it out. If it's not, I have to account for it. Now, why this is important, why this makes it easier, because if this is a constant, remember when you do antiderivatives, constants can go out front if it's being multiplied. So this is 1/5 antiderivative of 7, or w to the 7th dw. That's how it works when you have constants. You can throw them out front, and we can do the antiderivative. The antiderivative of w to the 7th is w to the 8th over 8. Right? You add 1 to the power, divided by the power. The 1/5 is still out front. That's just being multiplied. And then you have the plus c in the back. And now what I'm going to do next is substitute back in what w was. W was a 5x plus 2. I'm going to plug that back in. The 5 and the 8 are on the bottom. Those are going to multiply to give me 40. And there you go. And this is the antiderivative. Now, if you're not sure, again, multiply it. See if it works out. See if it actually works out to be the right answer. So, in fact, I'll do that. I'm going to change up the colors so you can see this here. All right, so doing the derivative, I drop the 8 out front. Again, I'm ignoring the 40 on the bottom because it's a constant. So dropping the 8 out front, subtract 1 off the power, and then take it times the derivative of the inside. The derivative of the inside is 5. So the 8 and the 40 will simplify to be 5 on the bottom. And then the 5s would cancel out, and I'm left with 5x plus 2 to the 7th power, which is the original problem that I started with. So it is the actual antiderivative. Again, it's by substituting. You're taking out the thing in the parenthesis and then doing the antiderivative and going backwards. It makes the problem easier to find the answer in the long run. Okay, we got 2 more problems here. This one's tough. I apologize on this one. This one uses a rule that we haven't seen for a while. In fact, I'm going to review that rule with you right now. The rule that we're going to be accounting for on this one is this rule. These kind of go hand in hand. The natural log of x. If you take the derivative of natural log, so let's say this is my function, right? This thing. And I took the derivative of it. So this would be f prime, right? I'm taking the first derivative. That's what gives you this. So the derivative of natural log is 1 over x. So that means the antiderivative of 1 over x is this. Okay? So it's, if you want to go back to the original problem. Now, I know that seems weird, like, why are you telling me that? It's going to be in this problem. We have to know that. That was one of our derivative rules we had. I'm going to leave that up there. So the w that I'm going to pick on this problem is giving me my x squared plus 1. It's usually always the thing in the parenthesis. Taking the derivative of both sides, that's 2x, and then the dx. Now on this problem here, the dx is there, the x is out front. This x can technically go right in front of the dx here, but the 2 is not accounted for. There's no 2 in that problem. So just like I said before, I'm going to divide this 2 over, put a 1/2 here. So I'm going to move the 2 over. That way, this part I can plug into this problem. I can plug this in for the x dx part, and you'll see that here in a minute. So on my integral, I have the x dx, right? This is over x squared plus 1. Okay, that's in parentheses. So this part up here is going to be my dw part, but it's going to be the 1/2 dw. And then the part on the bottom is that w. So 1 over w. And then the x dx part was the 1/2 dw. That's the part that I substituted in. That was the x dx part. Now I'm going to move the 1/2 out front like I did earlier because it's a constant. I can get rid of it. Okay, so here's where we're at. Now this makes sense for the rule I gave you earlier, that if you have 1 over a variable, the antiderivative of 1 over a variable is the natural log of that item. That's this part right here, you're seeing it. So the antiderivative is the natural log. So that's what I'm going to do here in a second. Let me get rid of all this stuff. All right, so the antiderivative, what we're coming up with for this is the natural log of w. It's the part that you threw on the bottom. And then we still have the 1/2 out front, and then the plus c. So that's the part I need to get to. Now I need to substitute out what my w was. My w was an x squared plus 1. And half is out front. This is the final answer. That is the antiderivative to this original problem. Now you're starting to see the glimpse of why we do this. When your problems are really complicated, you substitute things in so that you can actually find an antiderivative for this. Like on this original problem, if I didn't know this substitution rule, I wouldn't even know where to start. Because it's a quotient rule, and you're trying to think about, okay, what would the antiderivative be of this quotient rule? I wouldn't be able to figure that out without having to substitute and then making it a little bit easier to look at. Again, this is not simple. You have to, there's lots of moving parts. You have to figure out what part to substitute out, take the derivative of that part you're substituting out so that it's accounted for, and then go into the problem and actually do the work. So it's not simple. Let's go to my last problem here, and maybe this is starting to click, maybe not. I'm going to do a trig function here again. So hopefully you can see how this works. So on this particular case, I'm going to say my w is an x squared. It's always the part in the parentheses, that's usually what I always do. The derivative of that is dw, and on the other side it's 2x dx. So it's taking the derivative of both sides. Now in this problem, what I don't have accounted for here is I don't have that 6 accounted for. I have a 2 here. So I can do a little manipulating here just so you can see this. Here's what I'm going to do just to show you this. Cosine x squared, and then I'm going to break this up to be 3 times 2 times x dx. Alright, so now you're starting to see why I'm doing that. I'm breaking it to 6 because these are constants. I can throw this 3 out front and this would still be the same problem, right? Because constants can be multiplied out front and that doesn't affect anything on an antiderivative because constants would just stick around. And now you're starting to see that why I did that is because this 2x dx is right there. And that's my dw. That's why I did it. So here's what we're looking at. We're looking at this. 3 integral of cosine of w, and then the 2x dx is dw. That's why we did it. It's making everything look easier. The antiderivative of cosine is sine. Sine w plus c, and then that 3 is still out front. It didn't go anywhere. That's the antiderivative of cosine, because if I took the derivative of sine, I'd go back to cosine again. Alright, so we're not done yet. This is my antiderivative, and then I'm going to need to substitute out the w. So the w that I took out earlier was x squared. And there you go. This is the final answer. If you take the derivative of this, it would go right back to the original problem we started with. Again, I know this is not easy. It's one of those things that you need practice. But again, thank you for all those who are actively participating each week. I know this is probably the hardest week we've had. I didn't give you a lot of lead up to this one. I tried to do some antiderivative the last couple weeks, but this is new stuff. I'm going to submit some problems on the Google form so that you can try out. But again, it's one of those things. I just want you to try it. But again, first priority is your health, your family's health. Take care of each other. I miss you guys. It's kind of weird not going to class and kind of having discussions with you guys, but hope to see you guys real soon.